We are Al-Orouba Schools team and I am Assam Malhis, a student in the 10th grade and the robotics student for 2 years now. I have participated in 7 competitions and placed runner-up in the Arab Sumo Robots competition in Qatar. When electricity travels through a cable, it faces resistance, and when it travels inside interconnectors, which are really long, underground electricity transmitting cables that connect countries together, the amount of resistance is even more considerable, which wastes a huge amount of our electricity as heat loss. This increases the amount of energy we need to produce, which costs even more money, and increases the amount of fossil fuels burned to make up for the electricity loss. We researched multiple solutions for this problem, such as shortening the length of the cable, increasing the voltage, and even using superconductors as the material for the interconnector itself, but none of them proved efficient enough to justify the costs. We ended up choosing to cool the interconnectors using cooling gas inside a closed-loop system, and using water as a heat exchanger between the cooling gas and the hot interconnectors. And to not be wasting water, we will be taking the water used in this project from waste sources. And we named this system ETHLP, short for Electricity Transmission Heat Loss Preventer. We got the inspiration to research this project after researching the energy production problems that face our country, Jordan, and we found out that most of the energy that we produce simply disappears. In this project, we've utilized multiple parts, such as a water reservoir, water pump, and the solenoid valve, with a gas canister and a gas pressure clock. We chose R410A, or more commonly known as Puron, due to its efficiency and keeping in mind it's environmentally safe, non-flammable, and non-toxic. We've also used a 12-volt battery for power alongside 3 sensors, which are 2 temperature sensors on either side of the project and 1 water level sensor on this side. We've also used 2 relays to control our pumps and our solenoid valves. We've also used an Arduino Uno for controlling the system and an LCD display to display our sensor readings and temperature readings. We've also used a breadboard to make connecting wires easier. Inside of our water loop system, we've used a water reservoir filled with extra water that we might need in case of a leak inside the system. Then that water runs through to this pump, which directly speaks with this water level sensor, so that in case of a leak or the water level inside our system going down, it will pump more water into the system. For the cooling side of things, we've used this R410A cooling gas canister, and we've hooked it up into this pressure watch, which helps us pressurize and depressurize the gas we are using in this system. After that, the gas moves through this tube and into this solenoid valves, which either lets it in our system or not, depending on the reading we get from our 2 temperature sensors. The gas, if we need it inside the system, will be let in and go through this loop around into this valve that we either use to pressurize or depressurize the system once more. For the control side of things, we've used an Arduino Uno, which directly speaks to our 3 sensors, which are 2 temperature sensors on either side and 1 water level sensor. Then the readings go directly to the Arduino, where it translates them and shows them on our LCD. Depending on the readings, we will control these 2 relays that directly control the pump and the solenoid valve. And here we have the 3D model for our project. It was built using SolidWorks, which is a 3D modeling software used by engineers. Anyways, let's first talk about the water loop system. Here we have 2 tanks. We get our water from waste sources as to not waste any clean fresh water. Here this tank will be supplied with wastewater, and it would dispose the water inside the other tank, which has a filter on top, as you can see. Then, once we need water in the system, this pump will activate, taking the water from this reservoir into our loop. Going into the cooling side of things, here we have the Puron pipe. This pipe will be the intake for the gas. The gas will move in this direction, making a loop near the pump, then going all the way to the other side. Here we will have a valve so that we can pressurize and depressurize the loop inside our system. Anyways, let's talk about the sensor we are using. We have two temperature sensors on either side of the project, as to keep track of the heating and cooling on either side of our project. This pipe surrounding the Puron pipe will be filled with water as we mentioned, and we will keep track of the water using this water level sensor, which will be submerged in water. And here is our code. We first begin by setting both of our PWM pins 11 and 3 to 255, disabling our relays in the beginning of the code, so that our solenoid valve will stay closed and our pump will be disabled. After that, we'll initialize our LCD with its pins before giving a cue with a short 5-second delay to give our temperature sensors time to run. Going into the loop, we'll clear our LCD before typing a header that indicates the following value would be the temperature, before typing the value received from both of our sensors on pin 2. Then we move on to the water level sensor, where we begin by typing out a header to identify that the following value is from the water level, before reading the sensor's value and putting it through a map function to change its value range from 0 to 1023 down to 0 to 100 and printing its value. Going into the if statements, we begin by comparing the mapped value of our water level sensor with 85, and if it's under it, it would set the PWM value of pin 3 to 1, enabling it so the relay activates, thus turning on the pump and pumping more water into the loop. And if our condition isn't met, we'll make sure that the relay is deactivated by setting the pin's PWM value to 255. Lastly, we go through another if statement that states if our temperature sensor's value is higher than 15, to set the PWM of pin 11 to 1, enabling the relay on that pin, and turning on our solenoid valve, letting through the gas, thus cooling down our system. And of course, if our condition isn't met, we'll make sure that the relay is deactivated by setting the PWM of pin 11 to 255. Now, if our system is applied worldwide, it could save up to $186 billion yearly, other than breaking even in less than 4 years. It could also save up the amount of fossil fuels burned yearly, which have huge effects on the nature around us. Comparing our solution to a newly proposed solution of using N-doped lutetium hydride superconductor material in the interconnector itself, our solution achieves the same results while using less rare materials and saving highly on costs. We use multiple sources researching this solution, such as government-funded research projects regarding the proposed issue so we can get accurate figures, notable chemists from renowned universities around the country to be able to choose a suitable coolant to serve the purposes of our project.